1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with the information we will be sharing today. Now, without further ado, we'll be sending the 1324 room link, and then we'll pass it on to our presenters. Thank you so much, everyone.
So welcome, everyone. Thank you for joining us. So as you see on the screen, all those of you who are here to review for Math 1314, stay here. And on the chat, you can see that they put the link for those who want to do the review for the Math 1324. So we'll give a few seconds for that, and we'll get started. All right. So again, so today's session is to review for your second exam. So some of you either are about to take it this weekend or maybe Monday or Tuesday. So hopefully this helps. Okay, so your second exam is over chapter 2, and it covers sections 2.1 all the way up to 2.6. So please, if you have any questions as I go through the review, please raise your hand, put a question on the chat, and we'll get to your questions, okay? All right, so this section, I'm going to start off, it's from section 2.6. And it reads, consider the following. F of x is equal to 1 over x plus 3. So what we have here is a rational function. It's a function that is a fraction, yes? So on your homework, it asks you several things. So it asks you to state the domain of the function, and it gives a multiple choice key answer. Identify all intercepts. Find any vertical and horizontal asymptotes. And plot additional points and sketch the graph. Yes? All right, so let's go ahead and do, first let's find the domain of the function. So if we look at this, we see that, again, the function is a fraction, and there are some exclusions or some restrictions that the domain can have. And the reason for that is because whenever we're dealing with a fraction, we never want the denominator to ever be equal to 0, because if it is, we have an undefined function. So let's see, will this function ever become 0 for the denominator? And if we don't see it, we can set it equal to 0, right? We set the denominator x plus 3 equal to 0, and let's find if there's a value that we can place into x that will in fact give us 0. So if you can see with the algebra, it will confirm that if x is equal to -3, okay, we would get a 0 on the denominator, and hence the function would be undefined. So we can use any value for x except for this number, -3, right? So our answer on WebAssign would be all real numbers except when x equals -3. This would be our excluded number, right? Because again, this number would give us an undefined function. Okay. All right. So let's go to the B, identify all intercepts. So first we will find the x-intercept. So to find the x-intercept, we set y equal to 0. So remember that f of x replaced the name of for the variable y. So let's go ahead and do that. So 0 is equal to 1 over x plus 3. So let's go ahead and get rid of the fraction by multiplying x plus 3 on both sides. So when I do this, the x plus 3 divided by x plus 3, that becomes 1. And then x plus 3 times 0, well, that's going to give me 0. So this gives me 0 is equal to 1, which gives me a false statement. This is not true, right? So then what this tells me algebraically is that there are no x-intercepts. So on WebAssign, you would put in DNE, which means does not exist, okay? So let's go ahead and solve for our y-intercept. So to find our y-intercept, we're going to set x equal to 0. So everywhere we see x, we're going to plug in 0. So we have 1 over 0 plus 3. 0 plus 3 is just 3 after we simplify. So we have the fraction 1/3. So our y-intercept is when x was 0, our y value was 1/3. Okay?
Here's my laptop. I have it turned this way so I can keep back
Right.
at this.
So if I can have you guys please mute your mics, that way you
Yeah.
don't interrupt with the session.
No, it's touching. And the mouse was moving and
Okay.
it was on the task.
All right. So C, find any vertical and horizontal asymptotes. Okay. So let's do the easy one first, or what I think is the easy one, is let's find the vertical asymptote. So the vertical asymptote, um, to find this, okay, or what I tell my students is that restriction, right? The restriction on our domain. A vertical asymptote is this imaginary vertical line that the graph cannot cross or touch because we cannot use this value. This value or this line, right, represents a value that does not exist on our graph. Okay, so um, as you can see, we can solve for this by factoring our numerator and denominator completely to cancel like terms first. Okay? And then we can set our denominator equal to 0 to solve for the variable. Now, it's very important that we do that first step, that step number 1, to factor the numerator and denominator completely. Because if we get to cancel values, okay, that no longer is, that value no longer becomes a restriction on our domain. As far as when we list a domain, it will take into effect, but what happens is when we eliminate or cancel like factors from the numerator and denominator, what this creates are holes in our graph. So it will have a difference in our domain, but it will no longer be an asymptote, okay? That restriction. So let's look at this one that we were working on. So we solved the restriction on the domain. Again, we don't have to factor the numerator because the numerator is already in its simplest form, which is 1. And also our denominator is in its simplest form, which is just x plus 3. And we saw that when we set the denominator equal to 0, we said that x could not equal to -3. So lo and behold, we have the equation of the vertical asymptote. This is when the computer asks you, what is the equation of the vertical asymptote? Um, we solved for it. X equals -3. This represents this imaginary vertical line that our graph cannot touch or cross. Okay? All right, so again, when we go to our graph, this is -3, and we always represent our asymptotes as a dashed line. Here on the graph, it looks dotted, but again, we represent this as a dotted or dashed line on the computer. Okay. All right. Now, so find any vertical and horizontal asymptotes. We found our vertical asymptote. Now to find our horizontal asymptotes. Okay, so there's several cases to determine if we have a horizontal asymptote. So the first case says if the degree of the numerator is smaller than the degree of the denominator, then there exists a horizontal asymptote at y equals 0. And this will always be true, okay? When the degree of the numerator is smaller than the degree of the denominator, we will always have a horizontal asymptote at y equals 0. Okay, that's our first case. Our second case is if the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote by this rational expression, right? This fraction, where the fraction is the leading coefficient of the numerator divided by the leading coefficient of the denominator. Again, these are the horizontal asymptotes, so this would be y equals, right? And then our third case is if the degree of the numerator is larger than the degree of the denominator, then there exists no horizontal asymptote. Now, keep in mind that these are the cases to find a vertical and horizontal asymptote, but I'm going to get a little bit ahead of myself. Whenever we have this third case, if the degree of the numerator is larger than the degree of the denominator, then you are not going to have a horizontal asymptote, but what you may have is what's called a slant asymptote. And I wanted to mention this because, again, this is a little bit of review. So just so you can keep this in mind. Okay, so let's look at our expression. Okay, now if I were to look at my expression, okay, and I rewrite it like this. Okay, if I can rewrite it. Okay. Now I'm gonna write a 1 here, even though we don't usually include it, but I wanted to write my expression again because that way I can see the degrees of the numerator and denominator. So here on the one that we saw when we wrote this is our denominator has a degree of 1. We don't write the 1 here, okay? But the numerator, anything to the 0 power, this is going to give me 1. And that's the reason why I wrote this here. So we can see that the degree of the numerator is 0, the degree of the denominator is 1, so we have our first case. The degree of the numerator is smaller than the degree of the denominator. So hence, we have a horizontal asymptote at y equals 0. Okay, so again, it's this axis here. Okay, we represent this as a dashed line, and to change, so you can see the difference between the vertical and horizontal. Again, my vertical is the pink color, and my horizontal is the blue color. Okay. All right, so I found my vertical and horizontal asymptote. So what's next? And again, these are just side by side. So now let's find the intercepts, right? So we found the x-intercepts. We saw that did not exist. We have our y-intercept that it's at 0 and 1/3. We have a vertical asymptote, which is at x equals -3. And we have our horizontal asymptote at y equals 0. So let's plot additional points just so we can get a better idea of the graph. Now I like to believe that with this is pretty much enough because, again, the graphs that they give us on WebAssign are multiple choice. So they make it very, very easy for us to determine which is the correct answer. But again, for practice purposes, let's go ahead and pick a few points, right? So let's pick x equals -2. So if x equals -2, when I plug it into my function, here I have 1 over -2 plus 3. -2 plus 3 is going to give me a +1. So 1 divided by 1 is 1. Okay? So when x equals -2, y is equal to 1. Let's try a different point. Let's pick +2 for x. So when I put in 2 for x, I have 1 over 2 plus 3. 2 plus 3 is 5. So y is equal to 1 over 5. Okay? Then again, let's pick 2 more just to be safe. Let's pick x equals -4. So we have 1 over -4 plus 3 gives me 1 over -1. So 1 divided by -1 gives me a -1. And the last one, x equals -5. So this is 1 over -5 plus 3. -5 plus 3 is a -2. So we have 1 over -2, which is just equal to -1/2. So let's go ahead and plot these additional points. Okay. So let's go through them quickly here. So we have, this is when x was equal to a -5. My answer here was at a half. Okay. When x equals -4, my value was -1. When my x was -2, I had a 1. When x equals 0, y was equal to the 1/3. And when x was a +2, I had the 1/5. Okay, so if we try to mimic these, okay, when we're writing them, and I'm trying to do what you probably do on your paper, right? We try to connect these dots, and again, these asymptotes tell us that we cannot cross or touch these imaginary vertical and horizontal lines. And then if I go to this side of here, it comes very close to that line. Then I get close to my horizontal asymptote, cannot cross it or touch it. And again, this is the nice piece of it, right? When the computer did it. So Again, in WebAssign, they give us these multiple choice. So when we're looking at this one, okay, so it looks like this one here, they look very similar, but it's telling me here that my vertical asymptote is less than um, -5, and it looks like it's probably this one, right? But if we look at this one, it's not this one. This one's crossing our our x-axis here at x equals 0, right? This one here is crossing it at, looks like at 3, and this one is crossing it at -2. So I hope you see that it's obvious that our answer is this first one, right? That these really have nothing to do with our graph. Okay? So I hope this helps. Any questions on this first example? Very good. All right, so again, this is what you see on the computer again, and we went ahead and answered these. Again, the first one was a multiple choice. The x-intercept they wanted you to write as ordered pairs, and to find the vertical asymptotes as a list. Yes. So this is a different example. So let's go ahead and do this one. Okay. So we have 3x plus 2 over x plus 3. And we're going to answer the same questions as we did before. Okay, so we have 3x plus 2 over x plus 3. Again, do we have a restriction on our domain? And our answer is, if we don't see it, let's set the denominator equal to 0. So we have x plus 3 is equal to 0. And we see that if x is equal to -3, we're going to have a restriction. Okay, so this is our domain, all real numbers except for -3. So our answer is this one, this B part. Okay. Let's solve for the x-intercepts. To solve for the x-intercept, we're going to set y equal to 0. Okay. So we set y equal to 0, and let's solve for x. We multiply by x plus 3 on both sides to get rid of the fraction. Okay. This is going to give us 0 is equal to 3x plus 2. Let's solve for x. Let's subtract 2 on both sides. And then let's divide by 3 on both sides. So we see that x is equal to -2/3. So our x-intercept is at -2/3. And keep in mind that this will also be our equation of our vertical asymptote, because it's our restriction on our domain, right? So let's find the y-intercept. To find the y-intercept, we'll set x equal to 0. So everywhere we see x, we're going to plug in 0. Simplify, and we get 2/3. So our y-intercept, and I do apologize, this should be a y, right? Not an x. This is y. Okay, y is equal to 2/3. Okay. All right. So can we factor the numerator and denominator? Well, no, right? The numerator is already in simplest form. This one has a 3x, this term has a 3x, this has a 2. I can't take either a 3 or an x from both of these. And then the same with my denominator. It's already in simplest form, so it's already factored. Okay. So again, when we solve for the domain, we also solved for the vertical asymptote. The equation of the vertical asymptote is x equals -3. Okay. But what about our horizontal asymptote? So if we see here, the degree of the numerator here is 1. We don't write the 1. And then the degree for the denominator is also 1. So it gives us this case. When the degree of the numerator is equal to the degree of denominator, we have a rational expression, right? We have the fraction of the leading coefficient of the numerator, which in our case is 3, divided by the leading coefficient of the denominator, which in our case is 1. So then for our particular problem or function, we have a horizontal asymptote at y equals 3 divided by 1, which just simplifies to 3, right? So this is a horizontal asymptote at y equals 3. And then we have our vertical asymptote here when y equals -3. Okay. All right. So we have our x-intercepts, y-intercepts, vertical asymptote, horizontal asymptote. Let's go ahead and get some additional points just to help us out. So let's go ahead and pick the same points that we picked last time. Again, when f equals -2, I got a -4. When x equals 2, I got an 8/5. When x equals -4, I got a 10. When x equals -5, I had a 13/2. Now these, they help us, these fractions help us very little because again, in our graphs, it's very hard to graph these fractions, right? But again, these are just reference points to see where the graph is living, right? Or we can draw it, right? So this is the nice version of our graph based on these points. So we have our smooth curves that come very close to our asymptotes but never cross or touch, both here and down here. Yes. So then we look at our WebAssign multiple choice. Again, this first option has nothing to do with it. It's the vertical asymptotes looks like they're reversed, right? They're on the wrong sides. Same thing with this one. It's on the bottom instead of the top. And this one is, again, on the right side. So if we see here, the one that fits our graph is this option B, right? Or the second option, okay? So hopefully it's very easy to see the solutions on the graphs that the computer gives us based on our information. Okay. All right. Any questions? Very good. So let's go ahead and move on. Let's go ahead and look at this other example. So we have x squared minus 9 over x. Again, they're asking us for the same things. So let's go ahead and go through those. So let's find our domain. Okay, the domain of the function are any restrictions on our numerator, right? We never want the numerator to become 0. So this one's very easy to see that if x is equal to 0, okay, we have an undefined function or 0 is our restriction. We cannot use 0. So the answer would be all real numbers except when x equals to 0. And again, this is also the equation of our vertical asymptote. Okay. Let's find the x-intercept, set y equals to 0. Okay. So when we do this, we have 0 is equal to x squared minus 9. So hopefully you see that this is a difference of squares. So we have, and you could also use our square root property to solve that. We're going to have two x intercepts, right, at +3 and -3, right? So our x-intercepts are 3, 0 and -3, 0. Our y-intercepts, let's set x equal to 0. So when we do this, we set that we don't want 0 at the bottom, right? So what this is going to tell us is that there are no y-intercepts, right? The answer for y-intercepts does not exist because, again, we cannot have 0 on the denominator for our fraction. Okay. All right, so let's factor the numerator and denominator. And again, I had mentioned to you that the numerator was a difference of squares. This can be simplified as x minus 3 and x plus 3. And I always like to factor because you could always see without having to do any more math, you can see that the x-intercepts are if x was +3 and if x was a -3. These would be our restrictions. Okay, but again, we cannot cancel any like terms because again, we don't have any individual x's on the numerator. So there's nothing for us to simplify or cancel. So we can just move on and say that our vertical asymptote is x equals 0. Okay. Let's look at the case here. The degree of our numerator here is a 2. The degree of our denominator is a 1. So our degree of our numerator is larger, it's bigger than the degree of the denominator. So hence, there's no horizontal asymptote for this function. Okay. Now, again, later on, this will represent that it has a vertical asymptote. Okay. So now, as mentioned to you, yes, therefore this has a slant asymptote. Okay, there's one that exists. So to find the slant asymptote, you can either use synthetic division or long division. Now I like to use long division because I don't have to convert my quotient back to an expression. And when I use long division, I already have my equation, right? So let's go ahead and use synthetic division just to practice synthetic division on this problem. Okay. Now here, to do synthetic division, you are going to divide. In this case, I'm going to divide by the zero, by one of the zeros that I have. But when I write the synthetic division, remember we have to have a placement value for all our terms. Now here we have a degree 2 as a polynomial on the top, so we have to have 3 terms, and the term that I'm missing is the x term, right? The x to the 1 power. So to represent that, I don't have one, I'll represent it as 0. So this is 1 for the leading coefficient of the degree, which is 1, 0 for the x, and then my constant is a -9. So to do long division, I bring down my 1 and then I multiply. 0 times 1 is 0, and then I add 0 plus 0 is 0. 0 times 0 is 0, and I put it here. -9 times 0 is -9. Again, this is just a remainder, but what I'm looking at is only this portion here. Okay, this is what's going to give me my equation. And again, if I write my quotient back to an expression, this is really just x, right? When we do division, we lose one of the degrees of the exponents of the numerator. We started with a degree 2, and when we do division, we lose one. We subtract 1 to that. So in this case, we have that our quotient's just x. Again, this is just a remainder. We can write this as -9/0, which does not exist. But again, it does not play into my equation. And that's why I like to use the long division. But again, our slant asymptote is going to be given by y equals x. It's just this x value that I have. Okay. So if I were to graph this, okay, we have our x-intercepts, which we have 2. We have one y-intercept. We have a vertical asymptote. We do not have a horizontal asymptote, but we do have a slant asymptote at y equals x. Let's go ahead and plot some additional points. Okay. So again, using the same points that I had done before, just to get a rough idea as far as where the graph is. And again, these are my points. Again, I would try to connect these with a smooth curve or line, right? But if I use the computer to really graph these points, okay, they give me these points, right? And this is my slant asymptote, okay? Then I had my vertical asymptote at x equals 0, okay? So here, okay, when we look at the multiple choice again, the slant asymptote has the wrong slope. This has a negative slope. This one also has a negative slope. These two have positive slopes like mine, but let's look at mine has the curves where I have a vertical asymptote at x equals 0. This one here, okay, has the curves inside both asymptotes, right? So our obvious answer is this one, right? The C. Okay. And again, hopefully that you always see that they're always easy to see which is the correct graph on these questions. All right, so we covered all parts of our rational expression. So let's go ahead and look at a very common question that students get stuck on because we forget the rules, right? We forget what our book tells us on the end behavior. So let's look at this particular problem. Describe the left hand and right hand behavior of the graph of the polynomial function. And we have this function 12x cubed plus 6x, okay? So let's do a little review, okay, of the leading coefficient degree of the behavior of the graph. So first, if we have an even function, okay, and our leading coefficient is a positive number, the graph is going to rise to the right and left of the graph, right? It's going to be pointing up because it's a positive, right? It's positive and it's even. When it's an even function and our leading coefficient is negative, it's going to point or fall to the right and left of the graph, right? It's going to point down, right? Because our leading coefficient is negative. Now, what about an odd function? When we have an odd function, the way the book explains the behavior is that it's going to rise from the right and fall from the left, right? And I like to say that it's always rising, like we're always growing, growing, growing as we read the graph from left to right, okay? If we have an odd function with a leading coefficient of a negative number, the book describes this as it rises from the left and it falls from the right. But again, I like to read the graph from left to right, and I think it's always falling, right? Because it's negative, it's always going down. Okay, so we can answer, if we know this, we can answer our problem. So first, what we need to see is what type of function do we have? Do we have an even or odd function? And we can see by the leading coefficient, right? The leading for the degree, excuse me, the degree of the function is a 3. The 3 is an odd number, so this is an odd function. So since it's an odd function, it's either of these two behaviors. I have to now look at the leading coefficient. My leading coefficient is 12, which is a positive number. So it's going to have this behavior here, where it's going to rise from the right and fall from the left. So when I come to my multiple choice, I'm going to answer those two characteristics of this graph. The graph rises to the right and the graph falls to the left. Okay, and the computer likes to rearrange these and move them around for you to make sure that you understand what the behavior is. Okay, so hopefully these questions are much clearer. You'll ace your exams this coming week, right? Now let's also talk about the multiplicity, the zeros and multiplicity. Okay, so whenever a graph doesn't cross our axis, just touches it, okay, and as this is an even function, we see that we're going to have a multiplicity that repeats, right? Here we have a double zero. That's why the degree is 2. We have at most 2 possible zeros, right? So this is an even multiplicity because our 0 repeats twice. Here, when we have an odd function, our functions will always cross our x-axis at least once, and our multiplicity will be odd because it only will cross at one time. We'll have one number that we have the zeros for. Okay, so let's look at some examples. Okay, of finding all the possible zeros that a polynomial may have. And to do this, we use what's called the rational zero theorem test. Okay, and again, it's a test. It's not going to tell you the actual zeros. It's just going to tell you the possible zeros. And to do this, to apply the rational zero test, is you list all the factors of the constant term divided by all the factors of the leading coefficient. Okay, so as a review, our constant term is our last term. Usually, it's the number that has no variable, it's just the number. And the leading coefficient, again, is the one associated with the highest degree, with the highest exponent in our function. It's the number in front of that. Okay. So let's look at an example here. We have f of x is x cubed plus x squared minus 9x minus 9. Okay, so we see that our constant here is -9, but because we're going to be looking at all of the factors of it, meaning we're going to look at all the positive and negative factors of it, I am not interested in its sign. I'm only interested in its value, which is 9. Okay, when I'm and then the leading coefficient of this function, again, we don't write the 1 here, but there's a 1 here. This is a positive 1. And again, I'm not interested so much on the sign. I'm interested in its value and its factors. And we're going to look at all aspects, the positive and negative. So that's why I'm not interested in this sign. So again, the factors of 9 are 1, 3, and 9. The factors are just 1. But I'm going to look at all aspects. I'm going to look at the positive -1, positive -3, positive -9, and positive -1 for my leading coefficient. And then I do the division. I divide. Let's start with a positive. Positive 1 divided by a positive 1 will give me a 1. A positive 1 divided by a -1 will give me a -1. A positive 1 divided by a positive 3 will give me a positive 3. A -1 divided by a positive 3 will give me a -3. A positive 1 divided by positive 9 will give me a positive 9. And a negative 1 divided by negative 9 will give me a negative 9. Now, again, when you do this, we don't write the duplicates. If we have the numbers already here, you don't have to write them again. Please do not include duplicates so the computer will mark them wrong. Okay, so these are the possible zeros. And I know that from my knowledge of this function, this graph has at most 3 intercepts, right? This has at most 3 zeros at and at least it has 1. But look, the rational zero test gave me 1, 2, 3, 4, 5, 6. Again, these are just possible zeros. It could be that one of them is a 0, it could be 2 of them, 3 of them, or maybe none of them. These are just possible, okay? Just so you can get that straight. So they also tell us that we can to solve for one of the zeros, and that's the reason why we use the rational zero test. In order for us not to just randomly pick numbers, we can use these possible zeros to actually find a possible zero. And since we know how to use synthetic division, which is a quick way to find if it's a possible zero, and the indicator is that our remainder will be 0. If our remainder is 0, this means that this value is a 0, the polynomial. So let's start with the first one. 9 times out of 10, guess what? That first one is a 0. So let's go ahead and try 1. X equals 1. So again, synthetic division, I bring down my 1 and I multiply. 1 times 1 is 1. Then I add. 1 plus 1 is 2. Then I multiply again. 1 times 2 is positive 2. Negative 9 plus 2 is a negative 7. And I do have to fix this a little bit. Okay. This is a negative 9 here. Okay. So 1 times a negative 7 is a negative 7. And again, this is not, this is going to be negative 9 plus negative 7 is negative 16. But again, this is not 0. So this is that 10th case that first one was not a 0. So let's go ahead and try our next possible one. So x equals 1 is not a 0. So let's try our next possible. Let's try negative 1. Again, this last one is a negative 9, and I'll fix it as I go on. So we got, bring down our 1. Negative 1 times 1 is a negative 1. 1 minus 1 is 0. Multiply negative 1 times 0. Negative 1 times 0 is 0. So 0 minus negative 9 is a negative 9. Negative 1 times a negative 9 is a positive 9. And again, this I did do the math right. I just didn't write it. This was a negative. Doesn't let me write. Okay, there we go. So we have a negative 9 divided negative 9 plus 9 gives me 0. So what this is telling me that x equals negative 1 is a 0. And this makes us happy because we actually found a 0. And if we wanted to find the remaining zeros, okay, this is our quotient. And now our quotient is a quadratic. And now either we can factor it, or we can use a quadratic equation, or we can use our square root property to solve for x. Again, I like to use factoring, but let's go ahead and use the square root property. So set this equal to 0. So add 9 on both sides. This gives me x squared is equal to 9. Take the square root of both sides. So when I do that, the square root of the square, they cancel or eliminate, leaving me just with x. And plus or minus the square root of 9 gives me plus or minus 3. So my 3 zeros are the negative 1, x equals negative 1, x equals negative 3, x equals 3. Now in your computer, in your homework, if they ask you to list the polynomial as linear factors, well, you can get that from these zeros. It's just solving for 0. You set these, what made you get the zeros, right? So what I do is I add 1 on both sides. So my factor for this first one is x plus 1. This is my factor. Add negative 3, add a negative 3 on both, or add 3, excuse me, on both sides. This gives me x plus 3. And then on this one, it's already subtract a -3 on both sides. This gives me x minus 3. So these are my factors. So the polynomial as a linear factor, let me see if I wrote it. I did not write it. So let me go back here because there is a question on your homework on possibly test that to write the polynomial as linear factors, and the answer would be f of x is equal to x plus 1 times x plus 3 times x minus 3. Okay, and then again, linear factors means that all my exponents are a value of 1. Okay, what I've seen, especially on the homework, students write the x plus 1 times the x squared minus 9. X squared is a quadratic factor, it's not a linear factor. So it's been marking students wrongs for that one. So don't do that mistake on the test when it asks you for the linear factors. All right, so let's consider this function now and do several steps for this one, right? So we have a function x to the 4th power minus x cubed minus 6x squared, and list all the possible zeros. Again, we're going to use the rational zero test. List all real zeros and multiplicity. Determine the maximum number of turning points of the graph, and we'll sketch the graph. Okay, so let's go for it. First, let's write the possible zeros. So I know I have a possible zero at 0 because if I plug in 0 here, 0, 0, 0 is going to give me a 0. So we can just verify this by using the synthetic division. So again, I have a degree 4. I have the degree 3. I have a degree 2, but I'm missing the x and the constant, right? So this is the representation here. This is x and this is my constant. I got to make sure I have representations for all of my terms. Okay, so we bring down the 1. 1 times 0 is 0. Minus 1 plus 0 is -1. 0 times the -1 is 0. Minus 6 plus 0 is -6. 0 times 0 is 0. And again, this proves to me that we had a 0. But I did this because this way, now my quotient is no longer a degree 4, but it's now a degree 3. So what I can do is I can repeat. I can use my synthetic division again to simplify this quotient one more time. So I can have something that's a quadratic. In a quadratic, I can use my quadratic formula or factor to find my zeros. Yeah, so let's go ahead and repeat. Again, I have a cube, 2, 1. Now on this one, I'm just missing my constant, so I have just 1, 0. So if I use synthetic division again, again, I knew I was going to get a remainder of 0. But what is my quotient? My quotient now is x squared minus x minus 6. It's something I can work with to find all of the zeros, right? So for practice purposes, okay, I couldn't factor this one, or I could, but let's practice using the quadratic equation, which is stated by x equals -b plus or minus the square root of b squared minus 4ac all over 2a. In my function, a is 1, b is -1, c is -6. So when I plug these in, I get two x-intercepts, 3 and -2. And again, this would have been a lot easier. We would have factored, right? But it's okay. We like to practice using our formulas. So our possible zero was 0. Okay. Now I didn't use my rational zero test, and I do apologize because again, we could have just solved for the zeros based on that. By plugging in 0, we can get 0 here. So we have our zeros are -2, 0, and 3. Now let's determine the maximum number of turning points. Now our multiplicity here, this is an odd number of zeros, right? So we'll look at this a little bit closer. So here, if we see the zeros here at the 0, okay, we have 2 of them. So that means that we have a multiplicity of 2. Now, I say that I had 3 here, but our degree of our polynomial was 4. So there has to be that 4 aspect, right? That 4th number, and it's here. our 0 is twice. So what this means that at 0, our graph just touched, right? Touched and turned around. And then this one, we only have 1, so we have a multiplicity of 1. And 3, we only have 1, so that's just a multiplicity of 1. Okay. Determine the maximum number of turning points. So to do that, that one's very easy. We look at the degree of the polynomial. The degree of our polynomial is 4, and we're going to subtract 1 from that. So 4 minus 1 is 3. So this graph has 3 turning points. Okay. And so let's go ahead and plot. So these were our intercepts, right? And then we can use our right hand or end behavior to see how this is going to behave. We see that this is an even function and that the leading coefficient is positive. So that means that on both sides is going to point up. We're going to have like a W when we draw this, right? So when we draw, just to make sure how the graph really is going to look, we pick some additional points to get a better graph or idea of our graph. Again, we try to do a smooth line to graph this, and we have again this like W looking graph. Again, but if we do that nicely on the computer, we get this, right? And it would be easy to match with our multiple choice on our graph, right? So let's go ahead and look at this example. I wanted to show you that I can also use synthetic division if I have a complex number, right? You see here I have a complex number where we have 4 plus 2i. I also want to mention something. On your computer, whenever you're dealing with complex number, they're always going to ask you to write the answers in standard form. Standard form always means writing the real part first, plus or minus the imaginary. If you don't separate them, the computer is going to mark it wrong, and that's a wrong answer because standard form is always separated. It's always separated with the real plus imaginary, okay? So we have this function, x cubed minus 12x squared plus 52x minus 80, okay? I'm going to use synthetic division, but use my complex number to do this, okay? And it is possible, it's just a little work, but you can still do it. Okay, so I bring down my 1, multiply 4 plus 2i times 1. This gives me 4 plus 2i. So the negative 12, again, doesn't have an imaginary part, so I'm just going to add real with real, imaginary with imaginary. So the real part is negative 12 plus 4 gives me a negative 8. This has no imaginary, so 0 plus 2i is just 2i. Then let me do it again. 4 plus 2i times minus 8 plus 2i is going to give me negative 32 plus 8i minus 16i plus 42i squared. Let me simplify by combining like terms. And then I get negative 36 minus 8i. Then again, it's in standard form. I always want to write it like this. Real plus imaginary. So the real parts, the 52 minus 36 gives me 16. 0 minus 8i gives me negative 8i. Then multiply again. 4 plus 2i times 16 8i is going to give me this 64 minus 32i plus 32i minus 16i squared. And when I simplify this, I have 64 minus 16i squared. I combine my like terms. Again, to review, I left this one like this to remind you that I squared means that it's equal to negative 1. So negative 1 times the negative 16 gives me a positive 16. So 64 plus 16 is 80. Negative 80 plus 80 is 0. So I can reduce this function into 1. I started with a cube, so this is x squared plus negative 8 plus 2i x plus 16 minus 8i. Okay. Now I can do it again. I want to simplify this even further to get it into something that I can factor or simplify. So I'm going to run through the synthetic division, and I see that I have a remainder of 0. So again, if I write my quotient now, I have a quotient of x minus 4, which allows me to get my other 0, x equals 4. Okay? So again, you can use synthetic division for complex numbers. Any questions? All right, let's see here. Now, so to list our zeros, we had a 0 at x equals 0. We had a 0 at x equals 4 plus 2i, x equals 4 minus 2i. Okay, so these are our factors. All right, let's do this one. This one is a very, very question that students struggle with. And to solve for this one, what you're going to do is apply your linear factorization theorem. Okay, so let's read the problem. It says find the polynomial function with the real coefficients that have the given degree, the given zeros, and a solution point. Okay, so again, I'm going to use the linear factorization theorem to solve for this. The linear factorization theorem says this, that if I multiply all the linear factors together, I'm going to get the polynomial. And this is, I didn't write the theorem, but just really quick, I'm running out of time. But this is equal to a sub n times x plus c times x plus c dot 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 all the way up to x plus cn. Okay, so this is just you get all the linear factors. If you multiply them together, you get back the polynomial. Now a sub n is like your leading coefficient. Right now we don't know how to get it, but I'm going to show you that when this piece of information, the solution point, is going to allow me to find out what a sub n is equal to. So let's do this. So it says that I have a 0 at x equals -4. So x equals -4. The linear factor for this, again, is solving for 0, which is x plus 4. Then it says I have a 0 at x equals 1. X equals 1, I get the linear factor of this is x minus 1. I subtracted 1 on both sides. Now I, okay, I, always, we know that this has a, because this comes from a square root, there's always two answers to this, right? There's a positive I and a negative I. So I can write this as x equals I, x equals negative I. So I have x, my factor is x minus I and x plus I. Now if you see, if I put these all together, when I multiply these, x times x times x times x, those are 4x's. That's going to give me my degree. So let's go ahead and do that. Let's go ahead and start from the back here. So let's do FOIL. X times x is x squared. X times I is ix. Minus I times x is minus ix. Minus I times positive I is a negative I squared. Okay. Let's simplify this. Combine our like terms. So ix minus ix cancels, leaving me with x squared minus I squared. We know that I squared is a -1. So we have x squared plus 1. Now let's go ahead and continue multiplying. Let's do x minus 1 times x squared plus 1. This gives me x cubed plus x minus x squared minus 1. Combine my like terms and multiply times the x plus 4. I have all these things here. Let's simplify and condense. So we have f of x is equal to a sub n x to the 4th plus 3x cubed minus 3x squared plus 3x minus 4. Okay, so as we see, we have a polynomial already, but we're missing a sub n. That's where this is going to come into play, the solution point. This says when I plug in x equals 0 to my polynomial or to my function, the answer needs to be -8. So let's do that. Let's go ahead and do this substitution. That when x is equal to 0, my y is going to be -8. So let's plug in 0 for x. 0 to the 4th, 0 cubed, 0 squared, 0. So 0 to the 4th is 0, 0 cubed is 0, 0 times 3 is 0, 0 times 3 is 0, 0 times 3 is 0, 0 plus 0 is just 0, right? But 0 minus 4 is going to give me a -4, right? So I have -8 equals a sub n to -4. Let's solve for what a sub n is. And we do this by dividing by a -4 on both sides. And this is going to give me -8 divided by -4 is a +2. So this is telling me that a sub n is equal to 2. So I'm going to replace it here and distribute. So I'm going to distribute this 2 to this polynomial. and it's going to give me 2x to the fourth plus 6x cubed minus 6x squared plus 6x minus 8. And again, with this given information, I have the degree 4 that they had asked. This is the highest exponent. These are my zeros. I use those to use the linear factorization to get my polynomial, and then I use my solution point to get my leading coefficient, the a sub n. Okay. So questions on this? I brushed it a little bit because I wanted to make sure we had enough time. I finished with 5 minutes to spare. Does anybody have any questions? Need me to review something, go over? Anybody have questions that they've experienced that want to get ready for your exam coming up? If you don't, I want to remind you, you have links on the chat. You can get credit for the Tejano passport. Again, if you accumulate enough points, they give you a nice medallion that you can wear when you graduate. Okay. Also, we would love for you guys to do the short survey. Also, click on the link. There's some instructors out there that give you credit for coming to this happy hour and reviewing, or some of you are required to do tutoring. So this also counts as a tutoring grade if your class requires you to do tutoring. Okay, so on the link to get credit for that. If there's no questions, thank you for joining me today. If you have additional questions, please stay. We have some awesome tutors that are happy to help you answer any more additional questions you have. So thank you again for joining me.
Thank you, Mr. Carzales. Thank you, students, for joining us. And we would like to invite you to join us again next week for another Happy Math Hour presentation. Please remember to sign in using the attendance link. And if you have any questions, feel free to ask. I'll be stopping the recording now.